In this video, I will give an example of principal component analysis and factor analysis. Before you watch this video, please make sure that you have watched my other video called Principal Component Analysis and Factor Analysis. Click on the link below the video to go to the website and find more information on this topic. Okay, so in this example, we have data on gross state product from Latin, Carroll, and Green. And the data set represents 50 observations. So these are the rows in the data set, and they are US states, the 50 US states. And there are 13 categories of the different products: agriculture, mining, trade, manufacturing, communication, energy, and so on. And the data set represents gross state product expressed as shares. So this is how the data looks like. Okay, so once we have the data analyzed with principal component analysis, this is the first table that you usually encounter. And these are the principal components, the eigenvalues, and the proportion of variance explained. And here you have 13 original variables. And these are the different components that were estimated from 1 to 13 because there are 13 variables. And these are the eigenvalues for the different variables. And so here are the eigenvalues that are above 1 up to 5, and then the rest are below 1. And this is the difference between the eigenvalues. So the 1 is the difference between 3.24 and 2.24. The 0.28 is the difference between these two. And so on. The 60 is the difference between the third and the fourth component. And so here, if you use the R software, it also gives you the standard deviation, which is basically the square root of the eigenvalue. Okay? And so we can see that here the next columns are the proportion of variance explained and the cumulative proportion of variance explained. So we can see that the first component explains 25% of the variation in the data. So here we have 13 original variables, and only the first component can explain already 25% of the data. The second component can explain additional 17%. So the cumulative is 42. If you sum up these two numbers, that's a 42. The third component explains 15% of the data, so cumulatively 42 plus 15 is 57, and so on. So you can see that the first three components explain 57% of the variation in the data. The first five components explain 77% of the variation. And if you go all the way down to using all the 13 components, they explain, of course, 100% of the variation in the data. Okay. So now, how many factors or components should we retain for the rest of the analysis? And the Kaiser rule says that you should retain the ones that have eigenvalue above 1. Okay, so I'm going to plot these eigenvalues right here for the different components on a scree plot. And this is what we're going to look at next. So this is a scree plot. So this is the first component. It had a 3 point something eigenvalue. The next one had 2 point something, and so on. These are just above 1, and then the other components have much lower eigenvalues. So if you want to retain 5 components, that's okay. 1, 2, 3, 4, 5. You can do those with that have an eigenvalue above 1. Another rule is that you need to look where there's an elbow or a break, and you could kind of argue that the first 3 account for a lot of the variation already, and there's like a significant break, and these are now getting very close to 1. So you can also use 3 components, and I will use 3 components for the rest of the analysis just because it will be a little bit easier to interpret things. But again, 5 components is recommended, and you could use this as well. Okay, so here's the scree plots that I got in R. So instead of just having a line, R can produce them as a bar graph. So the same thing, if they're above the 1 line, you can retain 5, or you can see how there's a little bit more of a drop here. And this is the same scree plot. This is the scree plot in SAS, same thing. You can look at the ones above 1. And here SAS also produces the variance explained. So the first one explains about 25% of the variance, the first component. The second component was, well, less than 20%. The cumulative of this plus this is that point here. And so on. The third component explains that much of the variation in the data, cumulatively is that much. So you see, if you use all 13 components, you can explain 100% of the variation in the data. Whereas if you retain all of them, the last ones almost don't contribute anything to explaining the data because they're captured by the first most powerful components. So that's why the question is of how many to retain, and we decided we'll retain about 3 of the components. Okay. So the next thing that we can get from once we estimate principal component analysis is what we call component loadings. So these component loadings represent the correlation between the components and the original variables. So the original variables are 13 from agriculture, mining, all the way down to government. These are our original variables. And these are the components that we're trying to summarize the data with. And again, we decided that we will use either 3 or 5. So I've kept here the first 5. Here you can see if we use 5 components, what is the unexplained variation of the data. So with 5 components, we only have 27% of the variation that we cannot explain. So these numbers are pretty good. I mean, we can explain most of the variation in the data. With 3 components, it's not as clear. So for example, here, if we only use 3 components, we cannot explain 65% of the variation. That's quite a lot, actually. And here, we cannot explain 52% of the variation in the data, and so on. But so perhaps if you're writing a paper or research project, use 5, but I'm going to continue to use 3 in the example here. This means that I'm just going to disregard these last 2 components, and I'm just going to work with the first 3 components. So when we look at these component or factor loadings, one thing that we are interested in is the correlations. And we would concentrate on those loadings that are above 0.3 or less than minus 0.3, because like this one, for example, is almost uncorrelated, so there's no need to like concentrate on this one. And so here, another way in which we could simplify that table is just to show those components that have loadings above 0.3 or below minus 0.3. And the rest we can leave blank. Okay, so that would be easier to interpret. So this is what I'm going to do on the next table. I'm just going to not show these that have loadings that are less than 0.3. Okay, so these are the first 3 components. I call this the no rotation, because we don't have any rotation on these yet. And everything was eliminated below 0.3. So here you can see that the first component has very high loadings on mining, transportation, trade, real estate and services, the second component, and so on. So one of the issues that we have here is that in order to facilitate the interpretation, we may want to put a rotation on these factors so that we have the highest possible loadings on as few as possible variables to kind of facilitate interpretation. So one such rotation, orthogonal, is the Varimax rotation, and we can now estimate these 3 components. Now these are the factor loadings after rotation. And you can see that at least on component 2 now we don't have that many factor loadings that are above 0.3. So now you can say, for example, how do in component 2, you could say it loads very high on communication, real estate, and services. These are the loadings on component 1. Sometimes they could have a negative sign. So you can see that actually for some reason Stata gives you almost the same rotations here for both Varimax and Promax. And so here you can actually see that only this component has flip signs, so to speak. And that's okay, actually that's pretty much the same solution. It's just that one of the, if all the signs are reversed, that's pretty much the same solution. It's just a mirror image on this one. So usually these components or factors also would be named based on the highest loading. So if you look, component 2 loads very highly on these, you could come up with a name that reflects all these 3. And that's important if you have a survey and you want to name your components or factors. Okay, so here are the component loadings rotations, and here on the horizontal one we have component 1 and component 2. Now if you draw also component 3, that will be a 3-dimensional graph, so it's harder to represent. So I'm going to only represent component 1 and component 2. So for example, let's see, mining. Mining had a very high loading on component 1, actually it was 0.47, and almost no loading on component 2. So this is its location. And you can see that, let's see another one, services. Services, on the other hand, has a loading of 0.38 on component 2, so this is actually 0.38, and a loading of minus 0.38 on component 1, so you can see that loading is the minus 0.38, so plus 4 and minus 4 almost. And this is how you can see the original variables that we have, all the 13 variables, how they actually lie in the component space. Now after rotation, this is the Varimax rotation and this is the Promax rotation, you can see how they start to have a little bit different location. So what we want to do is some variables really high loading on one component, almost no loading on the other one. And so we kind of want them to be almost close to the horizontal and the vertical axis, if at all possible. So trade is one such variable. You see how highly it loads highly on one of the components, component 1, especially the trade. The trade here, trade W, but it has a very low loading on component 2. Okay, so that's a 0.39 loading on component 1, and the second one is less than 0.3. And so you can see how it's, this graph right here is structured differently. And these are the component loadings for the oblique rotation that we have. And actually one thing you can see is how, because component 2 was with minus signs, you can see how it's flipped. So agriculture is here high, here is low. It doesn't have to be, it could be anything, but actually this is, in this case, these two graphs are very similar to each other, just reverse images. Okay, so if we estimate factor analysis this time, we can actually look now at the factor loadings. And so here we can see these are the first 5 factors, and we again use the same scree plot to determine how many factors to retain. So we can retain 3 factors up to here, or we can retain all 5 factors here. And this is what we call factor uniqueness. If we have the 5 factors, this is the factor uniqueness. Or it means this is like the error term for this kind of variable that we have. And the factor commonality is this proportion here. So you could see that with 5 components, this is the factor commonality with 5 components. This plus this equals 1. And so the commonality is 1 minus the factor uniqueness that we have here. And so again, we can see how 5 factors have if we use 5 factors, they have very high commonality here. So that's a very good reason to use a factor analysis. With 3 factors, then we have a little bit different picture where we have the uniqueness is kind of high, so the commonality for them would be lower if you calculate 1 minus this column here. Okay, so one thing that we can do now is look at the different rotations also for factors. And here's the original no rotation for the factor analysis. And we see one of the problems is that too many of the original variables are loading on all of the factors. So it's very, very hard to interpret these results. So what we want to do is actually have rotations where they load on fewer factors as possible. Well, if we look at these rotations here, actually it's not, in this case it's not much fewer, but we want, in general, that's the case where we have them lined up a little bit better. Okay, so once you look at these rotations, you can also try to name the different factors based on the loadings. So for example, factor 1 loads very high on manufacturing and on trade, whereas say factor 3 loads very high on agriculture and construction. Okay, so so you can possibly name these, say, manufacturing and trade as factor 1, and say, you know, we have agriculture and construction here, and actually trade is also high on that. So this is probably not the perfect data for factor analysis, but this is how you go about naming these factors. And there's not a lot of clear groupings in this example. Okay, so another thing you can do again here is to represent the factor loadings on the graph. And again, they are, here we have factor 1 and factor 2, and you want to see how the original 13 variables are in the space of these factors. And again, the goal is, if you have rotation, is that they would line up along the axes here, and you would have very high loading on one factor and low loading on the other one, and vice versa. Okay. Now, what we can also plot here is you can plot the principal component scores for the first 2 components. So now, these are not the original variables, these are the observations in the data now. And so you can look at the data. We have 50 states, so these are the row in the data set. And this gives us the idea about the location of the observations in the principal component space. So this is the first component, that's the second component. And we see that actually Alaska and Wyoming have very high loadings on component 1. And actually they do have very high values on mining and transportation, which actually have to have very high loadings on component 1, and that's why they're like almost like outliers here. And that's the same thing for the PCA and for the factor analysis. We have these two as outliers. So it's nice to look at your original data and the observations and to see how they lined up. Okay, so this is the same thing that we have, but only in R, so it's actually not as clear of a graph. Okay, so another thing that we can do is called scoring coefficients for the components or the factors, and I put them here for the first three components and the first three factors. And these coefficients are used to predict the values of the three principal components or the factors for every observation in the data using the formulas that we talked about in the previous video. And so once you use these scoring coefficients, we can actually predict the principal components, the three principal components in the data. So this is how the data looks like. So these are the different states. We have 50 observations, and here the columns in the data sets used to be the 13 variables that we calculated these principal components for and the factors for. But you can now, instead of using 13 original variables, you can use these three principal components or factors. And now notice one thing is that, again, here's the first component. See how Alaska has very high loadings on that, and that's why the previous graph that we saw, Alaska was an outlier on the first factor or component, just because it has very high loading on that. Okay, so the final thing to do is look at the Kaiser-Meyer-Olkin measure of sampling adequacy. So you can request this in a computer software and then interpret it. And here we have that values are less than 0.5. So overall, the variables have little in common actually to warrant principal component analysis in our example. So probably not the right data set exactly to be doing principal component analysis, but this is how you would go about doing this with your own data set. And so, okay, so this is all I had about principal component analysis and factor analysis. Thank you for watching, and now join me to look at the programs, one of the three programs that I used to generate these results.